Yes, good afternoon, good morning, ladies and gentlemen. Nice to see that you're all interested in this presentation from NXP on 6G, beyond 5G. My name is Mark Thomassen from the business line Radio Power. 6G is a wide topic. I'll be talking about communications and mobility especially. Let's go back a little bit in history. NXP has a long history in innovation, many different topics. When we zoom in into a few key items, NXP has been established from two key founding companies, being Motorola, being Philips. Motorola, nice examples of the car radios of the very early 50s. In the 90s, Philips one-chip TVs. As of 2004, Freescale has been established. NXP has been established as the semicon parts of these companies. Moving to 2015, where NXP and Freescale have been merging. So what are key innovation topics, very important also for these talks, the 77 gigahertz car radar ICs, ADAS, so advanced driver assistance systems. 2019, ultra-wideband, a very important technology for ranging, indoor positioning. 2020, NXP opening the gallium nitride power fab in our Chandler facilities. 6G is very important. 6G, we target societal digital transformation goals as drivers for 6G. Let's go back a little bit to the left part of this presentation. 1G to 5G, very successful journey moving from the initial coverage driven deployments to 3G with the first data transmissions, 4G with a lot of data transmissions, and then 5G bringing it to the cellular network being everywhere. So there is reasons to believe 6G is a little bit different approach. We'll take a little bit different approach where we take 1G to 5G metrics-driven industry coming together, looking at the key performance matrix, the size of the solutions, the cost, the performance, the benefits, the power efficiencies. Very much metrics-driven. Then what we see today is, what are we doing with the network? The network is everywhere, so that's really ubiquitous. IoT, connected devices, but also being able to sense because of the presence of base stations, infrastructure, network everywhere. So that brings to another item, which is on the right side of this picture, purposeful networks. So what are we doing with the networks is very much a different question. So an example, and we'll come back on that later, is shown in this right-hand side here. 6G progressing support of, for instance, passive sensing on top of network localization principles. So the technology can be implemented, very advanced technology, to basically see what's happening around this infrastructure. Moving forward on a 6G purposeful network, what you see here is a depiction of an ecosystem. That's the green dotted box. 6G ecosystem based from left to right. We see different function partitions. From the left side, sensing and actuating, close to where things happen. To the right-hand side, the cloud, where things can be calculated, can be worked out. As an example, for instance, taken in automotive system, sensing, actuating at the cars, the cloud, for instance, used for training and improving algorithms, which can be used also inside cars. What is also important is the green part, radio access network and the personal connectivity. So many standards exist. Seamless multi-access continuity becomes more important. Come back on that later. There are multiple standards, ultra-wideband, Bluetooth, Wi-Fi. How does that all seamlessly connect to the cellular network is a key objective. So this is very much a full ecosystem perspective, managed network service, including artificial intelligence, to overview the happenings in that service. What is a key building block? In the middle you can see secure, scalable compute platforms. Scalable, very visible. If we go to the left upper side, the digital wallet, security of a small transaction to actually happen very secure is important. Going to the right lower side, the data management part, where large data transactions, large data processing is important. So very scalable. That's important that it is secure. But also, if you look a bit on the top side, on top of the right hand, intelligent, safe automotive with V2X, meaning vehicle to anything, more towards ADAS system, advanced driver assistance systems. This is driven from compute platforms which are safe. Driving is a key element and safety is a key objective there. So moving to the connectivity parts, the radio interfaces. The lower side shows many different services, applications, from media streaming at the right to robotics, smart city at the left. Very different applications, but in fact using as part of those applications quite a lot of connectivity. On the top part you can see the cellular network, 5G here, the wideband area network, but on the left side ultra-wideband is there, which is a secure ranging and indoor positioning technology. But also the, as we know them very well, Wi-Fi, Bluetooth, many standards on V2X, which is more local for time-critical functions, local at positions where car and infrastructure are coming together. So many different connectivity, wireless radio connectivity standards, important to integrate that fully into the cellular 5G network system. Switching a bit gear on a certain first part of this vision, looking at the trustworthiness of the system. I think trustworthiness is an important aspect more and more of networks. Has been always important, of course, but it's the trust people have that the networks actually do as they're intended to do, and that is under various conditions. The right-hand side giving some context, and this is borrowed from very good work from the Industrial Internet of Things Trustworthiness Framework Foundations. This model shows quite clearly how to map different trustworthiness aspects to systems. So trustworthiness, obviously, in the middle of this picture. Then what you can see is that the combination of safety and security is building quite a nice, complete, full circle of trustworthiness. Whereas at the top side of this model, you see humans, environments as targets, systems, operations as targets at the lower side. You can see many aspects as part of that, more the systems part, resilience. So really the system keeps on working even under adverse conditions. Reliability, which is a more intrinsic element of the system performance. On the top side, it's more the outside-in view, humans, employees, customers interacting with the system, environment, like nature, public infrastructure. So this is really a key model to keep in mind when designing the ecosystem, in this case for 6G and mobility. Looking at the left-hand side, let's build up that picture. What does this mean for 6G? In the middle, the fundamental, the core need of 6G, the core function, the core aspects the system can bring. So the data for productivity, for interactivity, for entertainment, very much in the core. Then let's look at what are dynamics today and tomorrow in the mobility environment for this communication system. Let's start at the blue circle, the lower end circle. IoT, network infrastructure densification, so intersite distances at cities already today are less than a kilometer. We think that will further shrink in order to give the capacity to the many users and the many data throughput needs which exist, especially in cities, which will carry the majority of network traffic. So that's a very important element, network infrastructure densification, really meaning that the base stations, the connections, the UEs, the user equipments are really ubiquitous, are everywhere. If you look at the right lower side, increased situational awareness, the sensors become very important. Many new use cases are being dreamt of, are being investigated, are being looked at. Many ideas on what can we do with situational awarenesses, very popular things, digital twinning. So this is coming together at this bottom side, and you can look at it, the combination of situational awareness and the fact that the base stations are everywhere. Can we combine those two functions together and make dual use cases? We'll come back on that, and we'll show that is indeed a very good direction under the umbrella of joint communication and sensing, where the communication clearly is taking care of bringing the data from A to B, and sensing is passive sensing, like radar sensing, so sensing of objects, of people, things happening around the base station, but also positioning, which is more a technology which is helpful to increase the localization accuracy, but then based on a link which is established as part of the network. We talked about the lower part, which is very much the communications pillars. The middle part, which is very much the essential block element. Sustainable targets. Sustainable are the 6G environmental objectives, the societal trends. Safety on the move, very important towards driver assist. So when we talk about driver assist, a future trend looking to get safety from autonomous driving. So the top part is very much the mobility part. Key trend, as we know from the last decade, is the electrification of vehicles. In itself, that's coming from the sustainability objectives, but it also comes with a lot of innovation in the automotive industry. Getting more interactivity from the car, but also entertainment in the car. So toward autonomous driving, this is a very important trend which drives up the 6G data need as well. In an end state, we could envision, and we're really not yet there, but that the car is also a device on the move where it is autonomous driving, so it can be used for productivity, it can be used for interactivity, entertainment, and then of course you will see that also more data will be exchanged with the car and with the network. So this is all in all a challenge on security, of course, to get the data connected, but especially I would say a real good opportunity to enhance the safety of the movements of the car, and that coming from the network of the future. Okay, in the next slides I will be talking a bit more on technical aspects. So first of all, technology, the radio technology. Later on we will discuss a bit more on the architecture parts, and after that we will also see some techniques which can be used for localization, for sensing. So at this slide you can see the radio technologies which have been used for 2G, 3G, 4G. So that's linked to LDMOS, lateral drift MOS devices, very useful for the 2G, the 3G deployments at the lower frequencies, the 800 megahertz, the 1.8 gigahertz, up to 2.7 gigahertz. So with 5G, also moving to gallium nitride as a key technology, working up to the today's frequencies, the 3 to 5 gigahertz, but also beyond that, very much a core technology, a core pillar of the radio base station. As part of 5G, also the new FR2 frequencies, 26 to 30, 37 to 47 are being deployed, being used, and a core technology which NXP has been bringing in place is silicon germanium BiCMOS to support the various functions, the beamforming functions at those frequencies. For 6G, we envision new frequency bands. Important that more capacity can be freed up from releasing further additional frequency. Industry is very much working on that. So these are frequencies which are on top of today's available 6 gigahertz, so the NRU, the new radio unlicensed, and on top of that 7 gigahertz. We think it will go up, even up to 15 gigahertz, all very suitable for gallium nitride technologies, massive MIMO, digital systems. For the systems at higher frequencies, we think further exploration is now really coming into the close to terahertz frequency range, 100 gigahertz, where large bandwidth become available, which is also a good opportunity for ranging, sensing, higher accuracies coming from detection through these very wide bandwidth, which potentially become available at 100 gigahertz. Yes, this slide shows a hardware configuration. On the right-hand side, it's an experimental system. It's a dual-use architecture. We do think when we combine communication and sensing, it is not a costly function addition. So the communications part is very much the base. So we think the communications is the superset requirement. Once that is established at the hardware level, also the sensing functions can be implemented. If we look at the value, first of all, the environment sense awareness can support the radio network performance itself. So understanding potentially larger blockers close to base stations can help in the beamforming algorithms. And the second point, sense awareness, of course, can be used for safety in itself already, but also complementary to vision camera observation, whereas the sense, like the car radar systems, is working under night when there is no light or under adverse weather conditions. So it's also complementary to vision systems. Looking at the complexity cost, same beamforming and scanning principles apply for communications as for sensing. System challenges, of course, are there. Radar sensing systems do require good coordination, especially in multi-static situations where the radar is transmitted in one base station, received in another, and the radar function is a combined function. That does require a good synchronization of the timing elements, because radar in principle is, of course, very much looking at distances from observing the timing, the flight timing of the signals. A second bullet is, of course, resource allocation, to allocate resources in timing and frequency between the sensing and the communication function. And of course also that can lead to mutual interferences, RX-TX, receive, transmit, but also between different parts of the system. When looking at the site acquisition, so the position where to put these elements, we think communication and sensing have very similar needs, because it's more driven by the frequency which is being used, and therefore that can be very well combined. As said, going a bit into the automotive architecture. So what's in the dotted box is the automotive architecture of a very high level view of that, of what is driving the safety systems, what is driving the parking assist or the lane assist functions. So the basis, the core, is very much the automotive sensors. There will be many sensors, radars on the car, in the front, in the back, in the side. There is an embedded processing function securing that the controls are being applied in the correct manner. And external signals, external information is being used. On the left-hand side, there is a number of use cases as we know it today. And this is coming from a white paper which was made by NXP, ABI Research together on the future of automotive connectivity. So the bold parts of that list are very much about safety. So first of all, environment perception for car safety, but it's also the HD, so the very detailed mapping of the environment of the car, the road, and what's happening there. The remote automotive services, and that can be for maintenance, it can be for training of algorithms of the car, which is the machine learning and the augmented sensing combined function. So these are automotive domain use cases with the bold parts on safety. If we look on the information coming into the system, marked with B, that is the inter-automotive signaling, V2I, V2X, which is more towards local and time-critical functions with the infrastructure or other cars for collision avoidance, for detection of happenings in the system. The data services are marked under C, which are basically non-time critical services, can be training of algorithms. And what's the new part is the joint communication and sensing, the localizing functions which can be embedded through the 6G network. So 6G network technologies which are important is then new spectrum, the sub-20 and the terahertz, especially with wide bandwidth. That would be very instrumental in improving these functions. Coming to JCAS, the joint communication and sensing, to add passive user sensing to the system on top of what can be done based on the links. And the improved localization for connected users cars is then a third element important for new technology. Yes, on this slide you can see 5G and 6G opportunities to enhance network localization. Some techniques. On the left-hand side we see a classical challenge for a navigation system, which is the so-called urban canyon scenario. You can see that there are a number of satellites in the air. The red marked satellites are blocked because the signals are blocked by the apartments, the bigger apartments. The orange satellite does have the system connected to the car, but you can see it's coming through a reflection, and that is actually giving an erroneous signal to the car. So the perceived location is at the red position, the red car position, whereas the actual location is blue. And so this is not intended and a potentially dangerous situation. So here a connection to a base station at the ground, on the ground, would then help to resolve this ambiguity in the GPS, so the classical 1.5 gigahertz based CPS system. On the right hand side we see complete new developments, courtesy to Professor Weimers from the Chalmers University in Sweden. This picture is coming from a summer school presentation, so greatly appreciated. What you see here is a car, a UE in the middle. There is a base station, which is the blue part, XBS. There are many the signals going to the car. One is direct side, the green. The other red marked signals are reflections. So these propagation scenarios also help to improve the localization principle, because what has been shown in this material from Professor Weimers is that we can resolve the positioning equation if we have enough of these propagation paths. So there is like 7 unknowns. The timing, of course, the timing bias between UE and base station is key. There are X, Y, Z, so 3 unknowns from the position of the car, but also the position X, Y, Z of the antenna. So when there are enough accurate, good propagation paths, this equation can be solved, and in fact, from one base station, an accurate position of a UE can be established. Then moving to the use case for what can we do with this. In this street cross-section, you can see that a potential dangerous situation is created. A car, which is at the right-hand side, is driving and wants to go to the left where there is a bicycle, which view from the car is a bit obstructed through this big truck. So a warning signal can be generated from the network, and that can be done from sensing, from base stations seeing what's happening, passive sensing of the cycle, and connected with the car, a signal can be created there. So this can be done through a link to the car. It can also be infrastructure-centric, such that signposts are being used, or the traffic lights, or warning signals. So many options to actually implement that safety. But the core is that the sensing of the cross-section is done more complete, allowing more and better safety functions. Then moving to the summary, we see very good opportunities to improve automotive safety in combination with the 6G network. It all starts with what we call the network densification, the fact that sensing and communication is ubiquitous. It does require further improvement of network localization, so link-based techniques, but also sensing techniques which are helpful for passive sensing. And especially high bandwidth, wide bandwidth, high frequencies will help to add resolution there. Clearly also the high rate connectivity from the cellular network is very useful and instrumental for like machine learning driving applications. All in all, we think NXP is well positioned to deliver on this very exciting field of 6G applications, along with other players, key players in this connected automotive ecosystem. On top of that, also from NXP, we have key radio technologies, the gallium nitride, the silicon germanium BiCMOS available to support these new frequency challenges. Thank you.